Well, thank you, and thank you all for coming. Just who I am. So I'm the director of the Center for Radiological Research at Columbia University, which is actually the largest radiological research center in the world right now, and the oldest. It was founded, in fact, by a student of Marie Curie back in the 1920s, and I'm actually only the fourth director since then, so we have longevity. So our topic today is airport screening, very, very topical. The first of the new machines was installed in Boston just a week or so ago. So I'm going to talk a little bit about what this imaging technology is in the general terms, and the concerns that we have about the risks associated with mass screening. So, let me see. Yeah, so we're talking about backscatter imaging, and backscatter imaging is used in all sorts of different scenarios. And basically, the idea is you aim some waves at the thing you're interested in, and in this case, it's laser satellite imaging. And what you look for are the reflections of those waves coming back to you. And on that basis, in different ways, you can reconstruct the structure of the thing you aimed at. In this case, these tall buildings. Another example is actually sonar. Here's the ship bouncing some sound waves back from this submarine and getting information about the submarine. So the imaging technologies we're talking about are essentially this. You send some waves out, you bounce them back off the thing you're interested in, which is the individual's surface, and try and reconstruct an image from that. So what sort of wavelengths would you be interested in for personnel screening? Well, there are actually two different technologies that we're going to talk about briefly. One, whoops, not terribly visible, but here's millimeter wave, and here's X-rays. And basically, these are actually part of a whole spectrum of waves called the electromagnetic spectrum, which includes visible light and radio waves and X-rays and UV and ultraviolet. They're all actually the same sorts of waves. The difference is in the wavelength or the frequency of the waves. You know about wavelengths and frequencies just from tuning your radio to different wavelengths. So this is a very broad spectrum of wavelengths, going from very long wavelengths to very short wavelengths. And essentially the difference between these is the amount of energy that's being carried. What waves do, in fact, is carry energy from one place to another. And the amount of energy that's being carried actually increases as you go down this table here. So X-rays are more energetic, essentially, than these millimeter waves. So here's a little video, actually, from one of the companies of what goes on in the millimeter wave screening technology. Basically, you have detectors, you have emitters and antenna inside this little capsule here, and you stand still, and they rotate around you, and ultimately you get a three-dimensional image of the surface of the body. And the sorts of images that we get, or that they get for millimeter wave look like this, and in principle it's pretty easy to detect something like explosives or a gun. And the corresponding X-ray backscatter technology, basically you stand with your hands up in between two big boxes here, and essentially the same thing happens, that you get X-rays are bounced off both the front and the back of you, and you get images which the viewer can see. And these are actually, how would you put them, blurred images, essentially. There are a whole set of different issues which I'm not going to talk about today, about privacy, that you probably are aware of, that not really in my sphere of understanding, so I'm not going to talk about those. But these are blurred images in which all the details have been removed of the individual, but hopefully enough information still to detect any explosives or any metal devices. So we've got these two different technologies essentially doing the same thing, bouncing waves off the body measuring the reflected waves and basically creating an image. I'm going to talk mostly about the X-ray backscatter technology, because that's the one that is being thought of for most deployment in the next year or two by the TSA. So we have concerns about the safety of X-rays in general. And why is that? Well, remember your high school physics. So here's an atom. So here's a nucleus, and here are electrons orbiting around that atom. That's orbiting around the nucleus. So what happens when an X-ray comes along? Well, basically what an X-ray can do is knock electrons out of these atoms. So here's an X-ray that came along, and the electron which was here got knocked out of the atom, and the X-ray bounced on and can actually do this to more atoms. And that process is called ionization. And ionization is a process of knocking electrons out of atoms. And that's essentially the process which is biologically harmful, because if you can knock electrons out of atoms, you can distort atoms, you can break molecules. And what's important here is that X-rays can do this, but other types of radiation, such as the millimeter wave radiations, can't do this. They don't have enough energy to knock electrons out of atoms. And that's why we're particularly concerned in general about biological effects of X-rays, because they can ionize atoms in a way that radio waves or millimeter waves or UV or infrared cannot do. So inherently, they are significantly more biologically hazardous than the millimeter waves. So, yeah, X-rays are very effective at breaking molecular bonds, and we're particularly concerned, of course, about molecular bonds inside DNA. And so what that can lead to with X-rays is damage to our chromosomes. And what we believe the general model of how cancer occurs is that chromosome damage in a single cell is the first of many, many steps that ultimately lead to cancer. So the first step in the road to a malignant cell is that the chromosomes get damaged, and then many other things have to happen over typically a couple of decades till ultimately you get a tumor. And certainly not all chromosome damage by any means ends up in a tumor, but chromosome damage is the necessary first step for a tumor. I'll show you a couple of pictures here of chromosome damage from our own work. These are actually radiation workers. This is a chromosome spread from a radiation worker. So, as you know, we have 23 chromosomes, and what we've done here is paint every one of those chromosomes a different color. So there are 23 different colors here. So in a normal set of 23 chromosomes, what you'd see is 23 different colors. But what you see in this picture, you see this purple and blue here, and you see another purple and blue here. So what has actually happened in this case is the radiation has broken this purple chromosome and this blue chromosome, and then the cell is actually very good at repairing chromosomal damage, and it does its best to join up the right ends. But what has happened here is that the purple piece has joined up with the blue piece, and the blue piece has joined up with the purple piece here. So now we have chromosomal damage, and this is called a chromosomal translocation, because some genetic information is now scrambled between this chromosome and this chromosome. Again, that's one of the first steps that we know of that leads to cancer. And so that within a chromosome you can get damage too. So what we've done in this case is we've taken a single chromosome, this is our chromosome number 5, and we basically barcoded it. We painted a series of colors along the length of this chromosome. Now, I'm not sure we can quite see here, but there is one band here, this purple band, which is simply missing in this case. So what's happened in this case, again, this is a radiation worker, is that the chromosome was broken. A piece of the chromosome actually got lost, and then it joined back together again. And again, this is the sort of damage that is the first precursor of a cancerous cell. So what we're going to be